Every now and then I have to dig back into my rock and roll roots. That's a little Led Zeppelin from my distant past. And since I want everybody to rock and roll on this first exam, I thought it only fitting to put a little rock and roll riff in there this time. Okay, so the test is mostly non-calculator, and I'm going to go over some of the types of things that you would expect to know from the non-calculator part of the exam. Some of this is really college algebra review material also that's kind of sprinkled in there a little bit. Okay, so first of all, we look at problem number one, and we're just seeing it's a function, and you're really looking at the vertical line test. Okay, so if you kind of look at this one, vertical lines are going to go through one point, and you also got to be really careful about this right here. Okay, that's a check there. It only goes through one point, and it keeps going through one point, and even at this break right here, it's going through one point. So that's definitely a yes. Okay, the next one at first glance appears to be a function, but there's a problem. Everything is passing the vertical line test here good, but the problem is once you get through this point right here, you're actually going through 2 points, because that's a solid bubble, that's a solid bubble, so it's going to be a no. So just kind of background information, you want to know what the graph of a function looks like, since we deal with that in calculus so much. Okay, here's another example, a piecewise function. You would want to be able to take a graph that I give you and write that as a piecewise function right here. One thing I want to zoom on this a little bit. It didn't come out real clear, but that right there is a hole. This is solid right there. I think you can see that pretty clearly. That's a hole right there. And then that's solid there. Now this is an example of a function. This would certainly pass the vertical line test. So if you kind of look at this, you can divide this up into 3 pieces. The first piece you have is you're looking when you're actually going to look at this as x is less than or equal to -3. So you're looking at this region right here. So you're looking at this part of the graph right here as your first function. So when we do that, we want to just name that line, and then we can kind of formalize this and put this together like this. So we're going to write f of x where you put our brace. The first piece is going to be defined from x less than or equal to -3, and that's a line, that's a constant function, that is y equals -2. So all we got to do is say -2. We don't have to say y equals -2, because we already got that. We already got that built in. That's what f of x is. Okay, the next piece we're going to look at would be this piece right here, and if you look at this, just kind of looking at the graph, you're open there, so that's going to be between the x value of -3 less than x, and then that's a hole there, so you're also not going to include x equals 0. So you're looking at x equals -3, x equals 0. Now this is a line, so you can tell it's a line. So we have y equals mx plus b. Okay, you can tell the y-intercept is 4 on that, and then the slope, you're going down 1 over 1. You're doing a rise over a run. So you want to know your slope idea there. So you're going down 1, right 1, down 1, right 1. So down 1 is going to be represented by -1. And then right 1 will be represented by +1. So you would end up with -1 over 1. So that slope is going to be -1. So that line is going to be -x plus 4. And it's going to be defined on the interval -3 less than x less than 0. You got holes at the end of those, so you got to pay attention to those less thans right there. Okay, then the last piece that we're going to have on here goes back to this part right here, which again is a line. So again, you have y equals mx plus b. Okay, the y-intercept clearly is 0. Okay, the slope, you're going up 1, right 1, up 1, right 1. So again, we're doing rise over run. For the slope, so that is up 1 to the right 1. So that means that's going to be a slope of 1 over 1. So that's going to be 1. So this is going to give you x plus 0. That actually just gives y equals x. So we just write x there. And then this thing is being defined from x equals 0 and beyond. Okay? And then you have a solid dot there, so you're going to have to say x greater than or equal to 0. So that's piecewise function. So I want students in their background, since we do piecewise functions so much in calculus, particularly with limits, to be able to write or graph a piecewise function. So that should be the answer to the problem. Okay, so moving to the next thing here on the next page. We want to look at graphing a piecewise function next here. Okay, again, calculator free is the idea. So we have 3 pieces on there. I expect students to be able to graph piecewise functions. Okay, kind of a background thing again. So what I like to do is I'm going to make 3 tables of values. The first thing I'm going to do is I'm going to focus on graphing this part. So what we have is we have y is equal to 3x plus 2. And we're interested on the interval x less than negative 2. So what I'm going to do is I'm going to make a table of values. I think that's the most accurate way to do this. And then we're going to have y equals 3x plus 2. We know it's a line, so all we got to do is get a couple of points. I'm going to go ahead and use negative 2, but you know you have an open bubble there because of the less than symbol. So what I do is I just plug it in. I just go y is equal to 3 times negative 2 plus 2. If you work out that arithmetic, that's negative 6 plus 2, so that's negative 4. And then we can take another number. We have to be less than negative 2, so let's go with negative 3, just kind of keep it simple. So we would have y equals 3 times negative 3 plus 2. That's negative 9 plus 2, so that's negative 7. So what we can go ahead and do now is we can go ahead and graph that. We're going to start by putting a bubble on negative 2, negative 4, and then we have a point negative 3, negative 7 that I can highlight there, and then I can sketch in that line that goes from those 2 points like that, and that'll give me the first piece of the graph like that. Okay, so that takes care of that. Okay, so that's piece number 1. Okay, now we'll go to the second piece, which is a linear function again. So the second piece, we're going to have y equals x. This time the interval is negative 2 less than or equal to x less than or equal to 3. Okay, it's a line. We only need a couple of points. I'm just going to take the endpoints. So I'm going to use negative 2, and I'm going to use 3. Now, both of those are included, okay, because of the less than or equal to. So that means these points are going to be solid dots, okay? So if you plug in, you're just going to have, okay, x is negative 2, you're going to get y is also negative 2. X is 3, y is also going to be 3. So what I'm going to do is I'm going to go ahead and plot those 2 points. So I'm going to be left 2, down 2, like this. So I should be there. Then I'm going to be right 3 and up 3, so I should be there. And then I can connect those 2 lines, or those 2 points, into a straight line. And then that will give us the second piece. So we're done with that. And then that leaves us with the third and final piece of this graph, which is just going to be back to this piece. So we'll do that. So the third piece is going to be y equals 2x minus 1, defined on the interval x greater than 3. Again, let's make a table of values. Is the safest way to do this. Start with 3. However, you're not including 3, so you want to make a little indicator that that's a open bubble. Now, it may connect with that. We're going to find out. So what we're going to do is we're going to do y equals 2 times 3 minus 1. That's 6 minus 1. So that's going to be 5. Okay, then all we got to do is take one more point. So it doesn't matter what it is. Let's just go with 4. We know it's a line, so all we need is 2 points. So we can go y equals 2 times 4 minus 1. That's 8 minus 1. So that's going to be 7. So now we can plot our 2 points. So we have 3, 5, over 3, up 5 with a open bubble. Then we have 4, 7. So I'm going over 1, 2, 3, 4, up 7. Like that. Then I can connect this like that to get the rest of my piecewise function like that. All right, so that would be how that piecewise function is graphed. Again, making tables of values. Be sure that you're very clear on the difference between the open bubble and the solid bubble. And again, this is a function, so it better pass the vertical line test. So make sure when you're done with your graph that you are passing the vertical line test because it's a function. Okay, so the next thing we're going to look at is, this is really change of base formula is what we're looking at. So the change of base formula just basically goes like this. If you had a log base b of some expression x, that's going to be equal to ln x over ln b, or you can write it as base 10 log of x over base 10 log of b like this. Now, since we're wanting to write this one with logs, we're just going to write this as ln of x over ln of the base 9. Okay, so we're going to do this a little bit later in the class, so it's pretty important that you know how to use that change of base formula, particularly in terms of the natural logarithm. So that's very simple. It's just knowledge of the change of base. I don't give you the change of base formula. That's something I expect you to know. Okay, the next background thing I want to look at is finding an inverse, and I'm giving you a one-to-one function. Okay, I'm having you do an inverse of something that's a one-to-one function. So what you want to do is you want to start by just writing it like this. Instead of using f of x, use y. And then you want to switch the variables. That's the first kind of key step that you do, is switch the variables. So we're going to change the y to x, and we're going to change the x to y. So we're going to do that. Then the second thing that you want to do is you want to solve the equation for y. So we want to focus on that step next here. Okay, so when we do that, we have y is equal to 9 over x plus 2. I'm sorry, I forgot to switch the variables. So let's switch the variables. I already did that. So we want to take this equation, x equals 9 over y plus 2, and let's solve that for y. One approach is to get rid of the fraction. So you could multiply both sides by y plus 2. Okay, on this side, that's going to give y times x plus 2 times x, and that's going to be equal to 9. Okay, now we need to solve this for y, so that means I'm going to subtract 2x from both sides. You can just move that to that side if you want to. So we have yx equals 9 minus 2x. Okay, then I want to get rid of the x, so I can divide both sides by x, and then that will isolate the y. So I get y is equal to 9 minus 2x over x. Okay, and then the last step is you just want to write the answer. And you want to write the answer like this. You want to say f inverse of x is equal to 9 minus 2x over x like that. Okay, so I'm going to write this answer as f inverse of x is equal to 9 minus 2x over x. Okay, there is a way to tell you're right on this problem. You don't necessarily have to do that. But if you wanted to check and verify, what you do is you show that if you do the composition of functions of the function I gave you with the inverse, then you should end up getting x. So you can do this if you want to. If you wrote down the original function is 9 over x plus 2. If you plug in your answer, since you're doing a composition of functions, 9 minus 2x over x, like this, if you work out the algebra on this expression, you're going to end up getting, you should get x if you do this correctly. So what I'm going to do is, since I have a complex fraction, is I'm going to multiply the top by x and the bottom by x, and that will give me 9x. And then if you multiply and distribute, the x's are going to cross out, leaving 9 minus 2x. Okay, that's a distributed there, and then plus 2x. Okay, you're going to notice what happens is that cancels. That gives 9x over 9. and that gives x. So that's a way to prove that your inverse is correct, if you choose to. Okay, moving on to the next page. Let's see what we got here. We want to solve an equation with a logarithm. We'll be doing some equations later on in calculus with logarithms, so we want to be able to solve some of the basic ones. So we have log base 3, x minus 4 equals 5. Okay, we got to write this in exponential form. So exponential form means to take the base raised to the exponent, the fifth power. The answer to a logarithm is an exponent. That's how I remember that. And that's equal to the argument, x minus 4. And then you can work this out. 3 to the fifth is 243. And you would have x minus 4. So you could add 4 to both sides. Okay, so you would end up having x is equal to 247. So that answer to that problem is going to be 247. That's the answer to the equation. Okay, now you can also check your answer. Anytime you solve an equation, you can check your answer. This is, to me, ultimately how students make much better sense out of these problems, is by learning to check. So I'm going to replace x with 247. And I'm going to see if that's equal to 5. Okay, so this is just going to be the log base 3 of 243. Okay, you could set that equal to a variable x. So that would be 3 to the x equals 243. And then you'd have to know how the exponent works on this. So x would have to be 5 because 3 to the fifth is 243. So you can check and verify that you have the right answer on that problem if you want to. Okay, the next thing is finding the average velocity. The average velocity is really a slope of a secant line. You don't have to really graph this or anything, but the idea is you're going to find a slope. So the slope formula, if you're finding the average velocity, you're applying the slope formula, which can be thought of as just y2 minus y1 over x2 minus x1. I wouldn't give you that formula. Calculus students are expected to know that by now. So what I'm going to do at the side is, the first thing I'm going to do is I'm going to work with x equals 4 and just evaluate. So I have y equals 3 over 4 minus 2. So that's going to be 3 over 2. Okay, so what that means is we get a point. X is 4, y is 3/2. We got to establish 2 points. Then I'm going to take the 10. So if x is equal to 10, I'll have y equals 3 over 10 minus 2. So that's going to be 3/8. So that establishes that we have a point when x is 10, y is 3/8. So you got to start by getting 2 points. Okay, now we're ready to plug this into the slope formula. So basically, it goes like this. You can think of this as x1, y1, and you can think of this as x2, y2 if you want to. It doesn't matter what order. So if we subtract this, y2 is going to be 3/8. Y1 is going to be 3/2. X2 is 10. X1 is 4, like that. Then you could get a common denominator. So this is 3/8. You could convert this to 8. So that means you'd have to multiply this by 4 over 4 to get 12/8. And then 10 minus 4 is 6. So what you would end up having then is you would have negative 9/8 would be the result of the numerator. And you're dividing that by 6. So you could just go 9/8 times 1/6. And you could reduce that fraction if you wanted to, like this. 9 over 6 reduces to 3/2. So you'd end up getting negative 3 over 16 as the average velocity. Okay, don't have to worry about the units. I didn't give you the units on that anyway. So what I'm testing you over is that you know that average velocity of given a function is the slope of a secant line that in this case would connect these 2 points together. So that should be the answer to that problem. Okay, so moving to the next one. Of course, the next thing we want to be able to do is to evaluate some limits, like we've learned. So the first thing is this one. The very first problem is just asking you, what is this point? What's the function value when x is equal to 1? So I'm giving you x is 1. When x is 1, which is here, you have a function value of -1. So in other words, what you have is this point right here is the point 1, -1. You're giving me the function value or the y value. Okay, part B is a two-sided limit. You have to know the notation we've learned. So we're going to look at x goes to 1, so I'm just going to kind of put a line through that. And if you go from the left, that limit's going to approach 1. If you go from the right, that limit's going to approach a different number. So we're going to say that that limit does not exist. Okay, now we're looking at the limit as x goes to 4. Okay, so we're looking at this vertical asymptote. So the left-hand limit on this clearly is just going to go up to infinity. The right-hand limit on this side of the graph is also going to go to the same place. So we can say on this that the answer is just infinity. Okay. Then we're looking at the limit as x goes to infinity, which just means what's happening to the graph as x gets infinitely big. So if you traced this out, okay, the bigger we get, the lower the value of x goes. So it's just, basically it's just leveling off at x equals 0. Or not x equals 0, y equals 0. So the value of that limit would just be 0. Okay, now we're looking at 1 from the right-hand side. So I'm going to erase some of this stuff that I've done over here. So if we're looking at the limit of 1 from the right-hand side, okay, this is where x is 1. So just close in from the right, and you're going to end up going to that y value of -1. Okay, the next one is a left-hand limit. So you want to get just a little bit to the left on the function, closing in at x equals -1. Close in. The closer you get to that bubble, the closer the function value gets to 1. So the answer to that problem would be 1. Okay, moving to the next thing, a little bit more with limits and continuity is what the next problem is checking you on, is continuity. Okay, so first of all, I've given you a graph that has some places where it's discontinuous. So you're looking for where it has breaks in it. The first thing is you would be discontinuous at x equals 0 because you have the break there. You would also be discontinuous at x equals 3 because you have the break there. And finally, you would be discontinuous at x equals 6. Okay, so you have a break there. Now, the other thing I want you to be able to do is to be able to tell me why it's discontinuous in terms of the technical definition. The definition of continuity, you have to be defined at a point. The limit has to exist. And I think that one, I actually typed that wrong on there. You're trying to give me the reason why it's discontinuous. So this actually, the third reason would be the limit as x goes to a of f of x would not be equal to f of a. So you're telling me which one of these conditions is going to be the one that causes it to be discontinuous, and there can be more than one. So if you start with x equals 0, and if you look at this part right here, at x equals 0, what happens on this is the function is defined. Okay, you're defined at that point 0, 2, so it can't be that. Okay, now look at the limit. The left-hand limit is going to a y value of 3. The right-hand limit is going to a y value of 2. So that means the limit does not exist. So that would be the reason on that. Okay. Now, 3 you don't really have to say. It's if the limit doesn't exist, then it can't be equal to the function value. The key thing is the limit does not exist. Okay, then the next one you have, or discontinuous at x equals 3. So the reason, first of all, you got to see if the function's defined. Okay, this is defined. Okay, we are defined at this point 3, 4. So it can't be that one. Let's see if the limit exists. Okay, well, if we do the left-hand limit, we're approaching 2. If we do the right-hand limit, we're also approaching a y value of 2. So the limit does exist on that. But the problem is, on this one, if we looked at the limit as x approaches 3 of f of x, that's equal to 2. And then the function value is equal to 4, so that would mean that this would be the third case, is this would not be equal to the function value of 4. So that's why that function is discontinuous at x equals 3. Then when you go to the next one, we're looking at 6. Okay, and again, the thing on that is, well, there's an open bubble. It's undefined. So this one would be condition 1. It's undefined. The limit exists on that, but it's undefined. Okay, and then the last thing we're looking at on this one is the two-sided limit. I guess there's two more things. The two-sided limit on this, if I erase kind of my little drawings there. So if we're looking at the limit as x goes to 6, right here, your left-hand limit is approaching 4. Your right-hand limit is also approaching a y value of 4, so the value of that limit's 4. And then you're going to give the intervals on which f of x is continuous. So you got to be kind of careful about, left to right, where does it start? So we're going to start at -8. And since that's a solid dot, we're going to put -8 there. Okay, and then it continues to be continuous. You don't have to break it up into two intervals. It's continuous there. It starts being discontinuous at x equals 0. So we're going to put a parenthesis there. Okay, then we pick up from 0, again excluding 0 because it's discontinuous there. Then at 3 it's discontinuous, so we got to use a parenthesis there. Okay, then we're going to go from 3 to 6, again using parentheses. And then finally we're going to go from 6 to 9, again using parentheses. However, at 9, that's an included point, so we would be continuous there also. Okay. Now, I overlooked one thing, and this is something that I need to be careful about. These endpoints are also parentheses, and the reason is they would fail to meet the definition. And so like if you looked at 9, okay, the limit would not exist because there's not a right-hand limit to that. Same thing here, this limit would not exist because there's not a left-hand limit. So you got all parentheses on that. The endpoints are really not considered to be continuous, although this one is considered to be right continuous, and this one is considered to be left continuous, like we talked about. Okay, so let's see. The next thing at the bottom here says you're given this limit. Let me write this out a little clearer. So it's saying the limit as x approaches 0 from the left-hand side of f of x is equal to some value L1. And you're also given that the limit as x approaches 0 from the right-hand side of the same function is equal to L2. Okay, or L, what does that say? L1, I guess that says LR is what that is. Okay, can't see very good sometimes. Okay, so it gives that. It also gives that these are the same. So those two things right there are the same value. So what this means is if the left-hand limit and the right-hand limit approach the same value, then that means the two-sided limit is also going to exist. Okay, so it says which statement's false. Well, this is true because this is a two-sided limit. Okay, that's going to be true. This is also a two-sided limit. That's going to be true. They're both going to approach the same value, but does not exist. The limit does exist, and again, this is a two-sided limit. Since the left and right hand approach the same value, that means the limit does exist. Okay, so that's something we've learned. Okay, moving to the next thing. Another thing I expect you to be able to do is a difference quotient. Okay, for different types of functions. So let's do a difference quotient on this one. So we have f of x plus h minus f of x all over h, and we're going to go ahead and crunch that out. We're not going to do a limit or anything. We're just doing a difference quotient. So what you have in here is always when you set this up, just kind of draw two big brackets and the whole entire thing over h. So the first thing is f of x. F of x goes there, And f of x is just what I gave you. So that is going to be 2x over x plus 2. And then f of x plus h goes here. So all you're doing on this is you're modifying this by replacing these x's with x plus h's. So you would have 2 times x plus h. Okay, then in the denominator, you're going to have, again, x plus h, excuse me, and then plus 2. Okay, so we have everything set up. Now, what I'm going to do is I'm going to just do a little simplification. You could certainly go ahead and multiply that out if you want to, and then you could just write this as x plus h plus 2, which is what I'm going to do. So I'm going to write this as 2x plus 2h in the numerator, and I'm going to write this as x plus h plus 2 minus 2x over x plus 2, and then all over h. So now the focus becomes we need to get rid of these two denominators. So the way to do that is to multiply by, you're going to multiply by x plus 2 to get rid of this. But then you also have to multiply by x plus h plus 2 because it's a totally different factor when you do that. And you have to do this to the top and bottom. So I'm going to draw a bracket around this, and the numerator gets multiplied by x plus 2 times x plus h plus 2. I'm going to put that over 1 for emphasis, really. And then the denominator has to be multiplied by exactly the same thing to keep from changing the expression. So you're doing a distributive property. You're going to multiply that by that. You're going to multiply that by that. Now I'm going to write out the step on here. You don't necessarily have to do this, but if you need to do this, then certainly take the time to do this. So I'm going to have 2x plus 2h over x plus h plus 2 times, and then I'm distributing this, so this is x plus 2 times x plus h plus 2, like that, all over 1. Then I'm going to have minus 2x over x plus 2. Then I'm going to multiply this by x plus 2 times x plus h plus 2 over 1. And then don't forget about that denominator because it certainly hasn't disappeared. So you have h times x plus 2 times x plus h plus 2 like this. Okay, so we need to work with this mathematical expression. What's going to happen is you're going to have some cancellation. So you're going to have that canceling and you're going to have that canceling. So we can go ahead and write the next step as 2x plus 2h times x plus 2 is what's left over there. Okay, and then over here we have 2x times x plus h plus 2. And then the denominator we have h times x plus 2 times x plus h plus 2. Okay, then we're going to need to go through and multiply this out. So I'm going to do the FOIL here. So I'm going to multiply these two things out, then I'm going to multiply those two things out. You'll probably have a lot of things that cancel. So FOIL, the first thing you're going to have 2x to the second plus 4x plus 2hx plus 4h. So I just did 2x times x, 2x times 2, 2h times x, and then 2h times 2. And then I'm going to do a distributive property here to get minus 2x squared, minus 2xh, and minus 4x. Okay, and then that's going to be all over h times x plus 2 times x plus h plus 2. Okay, like that. All right, now let's go ahead and see what cancels. So the 2x squareds cancel, the 4x's cancel, and the 2xh's cancel. So you're left with 4h in the numerator over h times x plus 2 times x plus h plus 2. Now you can take out the h's, and then that would be your answer. Okay, so right here would be what you're left with. Then we can write that answer. Okay, so that answer is going to be written as, we just have a 4 in the numerator, and then the denominator we have x plus 2, and then we have x plus h plus 2. Now we're not doing a limit, so don't let h be to 0. We're not doing the derivative on this yet. We're just simplifying the expression for this first exam. Okay, so moving down, now we're going to look at some basic limits. Okay, so what this one is testing is we learned that if you do the limit as x goes to a of some constant, then the answer is just the constant. Okay, if you don't know that, I mean, just reason it out, because all this is really saying on this is if you looked at a graph of this, and you sometimes you forget things and have to reason it out. All in the world this is saying is you have a horizontal line, y equals 10. So the limit has to be 10. Okay, so you can do that if you have to. Okay, the next thing that we're doing is this is a linear function. So you're really doing a linear function. So all you got to do is plug in. We know that a line is always continuous. So all that you have to do if you're doing the limit as x approaches some linear function is you just do arithmetic. So you're just going to plug in the -3. You're going to have 4 times -3 minus 8. So that's -12 minus 8. So that's equal to -20. So that would be the result of that problem then. Okay. So those are simple limit exercises that we've learned how to do. Okay, now the next one is a polynomial. Okay, so another thing we learned on this is a polynomial function in a factored form. So if it's a polynomial, we also know that polynomial functions are always continuous. So really all you got to do on this is just do some arithmetic. So we're going to do the limit as x goes to 2 of x plus 1 squared times x minus 1 to the third. Okay, so that's going to evaluate to give 2 plus 1 squared times 2 minus 1 to the third. So that will be 3 to the second times 1 to the third, which is 9 times 1. So that's going to be equal to 9. Real simple arithmetic problem. You don't want to be missing problems like that. Okay? Okay, so the next thing I do is I want to make sure that you know all of your limit laws that we learn. You refer back to your notes and look at those limit laws. I'm going to pull those up in just a minute. Okay, so I am going to, like magic, paste all of these limit laws here so we can refer to those as needed. So this is really what you want to be sure that you know is all of these limit laws right here. We have the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. You can bring a constant out of a limit. So if you have a limit of a constant times a function, the constant comes out of the limit. The limit of a product is the product of the limits. Limit of a quotient is the quotient of the limits. And the limit of a function to a power is the limit of the function to that power. Same thing goes with fractional powers. So you're trying to write this out carefully, and part of what I do on a problem like this is I like you to be able to carefully write out your steps. I grade you for your steps on this. So I've given you basically 2 limits. I've given you the limit f of x as x approaches 8 is 4, and I've given you a second function, g of x, that limit as x goes to 8 is equal to 2. So you're going to show your knowledge of the limit laws on this. So what you want to do is you want to write this like this. First of all, you want to write down the problem that I've given you. So we're doing the limit of 8 of 10 f of x minus 4 g of x all over 3 plus g of x. And you want to show that you understand how these limit laws work without just plugging stuff in. Okay, so first thing is we have a limit of a quotient. So by Rule 5, we would say the quotient of the limit. So we're going to say the limit as x goes to 8, not infinity. I think my head must be turned sideways or something. Okay, so we have that. So we're going to have the limit of 10 f of x minus 4 g of x. Okay, that's the limit of the numerator. Then we're going to divide that by the limit of the denominator, which is 3 plus g of x. Okay. Next thing we have is a limit of a difference. So the limit of a difference is the difference of the limits. So we're going to write this numerator as limit as x goes to 8 of 10 f of x minus, and let me erase this and bring this down a little bit so it's going to be a little clearer. So we're going to have the limit as x goes to 8 of 10 f of x minus the limit, there I go writing infinity again. Okay, need to turn my brain right side up. Then I have the limit as x goes to 8. There I go again. Oh God, senility here. Okay, then I've got 4g of x. Okay, like that. Okay, then I'm going to do the same thing at the bottom. I know the limit of a sum is the sum of the limits. So I write this as the limit. Let's be careful this time. Can he do an 8? Yes. Limit of 3 plus the limit as x goes to 8. Almost drawn infinity again. Okay, so we got that. Okay, now we're going to use this constant rule. Okay, so we're getting close now to being able to finish this up. So we can take a constant out of the limit. So we're going to say 10 times the limit as x approaches 8 of f of x. And that's what we're trying to do, is just get the limit of f of x. Minus, again, bring the 4 out. So we'll have 4 times the limit as x goes to 8 of g of x. And then this is going to be all over. Well, this is a limit of a constant, so we just leave that like it is. Okay, and then we're going to leave this alone like that. So what I'm trying to see is that you understand how your limit laws work. I want to see those steps. Now you're ready to plug stuff in. Because what you have is a limit of f of x. And see, that's given as 4. So that's going to become 4. You have a limit of g of x. And that's given as 2. So these things can all be put together like this. Now your final answer, you're going to write 10 times, the value of that limit is 4, minus 4, the value of that limit is 2, and then we know the limit of a constant is just the constant, so that's 3. And there I go writing in. This is cracking me up. Oh God, okay. All right, so that's the limit of 8, like that. I have to turn my head sideways sometimes when I use this tablet. So anyway, that's supposed to be limit of 8. Okay, so we got 3 plus 2 like that. Yeah, now really we're plugging in. I mean, yeah, there's no doubt that that's a 4, that's a 2, that's a 2. So you're doing 10 times 4 minus 4 times 2 over 3 plus 2. But I want you to show that you understand the limit laws. I don't give you the limit laws, you need to know those. Okay, so that would be 40 minus 8 over 5, so that's 32 over 5 should be the answer of that problem then. Okay, so that you want to show me that you can write out limit expressions in that way. Okay, the next problem is applying the squeezing theorem. Now, at this stage, it's not your job to figure out two functions that f of x is squeezed in the middle of. I'm giving that to you. So the idea is, since we know that x to the third, that the function is squeezed in the middle of these two functions in this interval -1 to 1, what we can look at is we can do the limit of these endpoints. So we're going to do the limit of x to the third as x approaches 0. We're approaching 0 because that's what the question is. Okay, so we're going to do that. That's equal to 0. Then we're going to do the limit of x. So we're going to do the limit of x as x approaches 0, which is also 0. So from the squeezing theorem, then what we can conclude, we would say, therefore, the limit of as x goes to 0 of f of x would also go to 0. So the answer to that problem is 0. That's just an application of the squeezing theorem. You're going to know to use the squeezing theorem. If I don't give you the function, so there's no way to figure it out unless you had knowledge that I'm applying the squeezing theorem on that then. Okay, so that's the idea. Okay, next one we're going to look at a limit on this. This is probably one that we want to just start by plugging h in and let's see what happens. We do not have a 0 over 0 limit here. So we're just going to plug into the expression. We're going to have 2 over the square root of 3 times 0 plus 4. That's what's under the radical, and then plus 2. Okay, so we're going to have 2 over square root of 4 plus 2. So that's going to be 2 over 2 plus 2. So that's 2/4. So that answer is 1/2. Okay, sometimes on a limit you just plug in the expression, and that'll give you an answer. That function's not discontinuous at h equals 0. It's just equal to 1/2. So all you should have to do on that is plug in that limit. Okay, next one. These are ones that are real important, I think, to study. Sometimes students struggle with these unless they have a graph to refer to, and on a piecewise function you don't have to look at the graph. So what's going on this problem is you're looking at the limit. You're looking at a left-hand limit when x approaches 4. So you're kind of, this is broken up into 2 parts right here. Okay, you want to go ahead and see what happens on this. And this is a left-hand limit, so when we're to the left of 4, we're on this function right here. So what we're going to need to do on this is we simply need to do the limit as x approaches 4 from the left-hand side of 16 minus x squared. We know that we can come from the left of 4 on this function because this function is defined from 0 to 4. So all we should have to do is just plug this in to get 16 minus 4 to the second. So that's going to be 16 minus 16. So that should be equal to the square root of 0. So that should be equal to 0. So you could do the left-hand limit on that. If you were doing the right-hand limit, and I'll just kind of add this on here, if you were doing the right-hand limit, okay, then you'd have to plug into this, because if you're to the right of 4, you're on this thing, so that would be equal to 4. Now the two-sided limit wouldn't exist, because notice the left-hand limit is 0, and then the right-hand limit's 4, so the two-sided limit would not exist, okay? So pay attention to the piecewise function, and then you can determine the limit that way. This next one, what you have is, again, we're looking at a right-hand limit as x approaches 1. So on the right of 1, on the right-hand side, x is greater than 1, you're defined to be on that line. Okay, so you're going to do the right-hand limit of 4x plus 6. So to solve this problem, you're just going to do the limit as x approaches 1 from the right-hand side of 4x plus 6. So all you need to do, that's a line, simply plug in and evaluate. So you're going to have 4 times 1 plus 6. So that's going to be equal to 10. Okay? If you did the left-hand limit on this problem, x approaches 1 from the left side, then you would have to go to this function. And you'd have to plug in like that. So that would be negative 5 times 1 plus 5, which would be equal to 0. Okay? So you want to be careful. That's just basically testing that you understand how piecewise functions work, which piece you do the left-hand limit of and which piece you can do the right-hand limit on. Okay? Okay, now we're going to get into some limits that are done algebraically. The first thing that you generally want to do is plug in the number and see if it's a 0-0 limit. Okay, so let's start by just doing 4 squared minus 16 over 4 squared, like that, minus 6 times 4 plus 8. So that's going to be 16 minus 16 over 16 minus 24 plus 8. So that's 0 over negative plus 8. So that's 0 over 0. So that is a 0-0 limit. So that means we need to apply some algebra and then reevaluate the limit, because the limit is going to exist. So what we're going to do is we're simply going to factor both the numerator and denominator. So the numerator is a difference of 2 squares. So you need to just factor x plus 4 times x minus 4, like that. Then the denominator is going to factor as a trinomial. That denominator is going to factor as x and x. And then you're looking for two numbers that multiply to give 8 that add up to 6. So that's going to be 4 and 2 with 2 minuses, like that. Okay, so you got your factoring correct. You want to make sure every time you factor, you check it. So then that's going to cross out. Then you would simply reevaluate the limit. So you're going to be left with the limit as x goes to 4, And what you're left with is x plus 4 over x minus 2. So plug it in, you're going to have 4 plus 4 over 4 minus 2. So that's 8 over 2. So that would end up being a value of 4. So that's the answer to that limit. Okay, so the next example is very similar. We're going to have to probably do some factoring. First of all, plug the 1 in. So you'd have 1 to the 4th minus 1 over 1 minus 1. Pretty clearly that is a 0 over 0 limit. So we need to start, when we're working out the details on this limit, is we need to go ahead and factor the numerator. So we're going to have a difference of 2 squares. So that's x and x. That's a plus 1 and a minus 1 over x minus 1. Now, this one still factors. This one does not factor. You can't factor a sum of 2 squares, so leave that alone. So you're going to have the limit as x approaches 1 of x squared plus 1. Now, you can factor this as x plus 1, x minus 1 over x minus 1, and then you're going to have the cancellation that you expect. Now you can go ahead and evaluate the limit. So you're going to have, in the first parenthesis, you're going to have 1 to the 2nd plus 1. In the leftover parenthesis, you're going to have 1 minus 1. So that will be 2 times 0. So the value of that limit is going to therefore be 0. Okay? You'd end up having a bubble in this graph at x is equal to 1. Okay, so that's arithmetic and factoring. Your skills have got to be up to par on both of those. Okay, moving to the next page, we're going to work a little bit more with some limits. Okay, so now we're going to kind of get into what's going on with rational functions and their limits. The thing that you have to know on this problem is, first of all, you have a rational function. And you got to know what a rational function is, and you got to know some of the key things on this. So if you have a rational function, typically you got to look at your asymptote. So you're interested in a limit around a vertical asymptote. So clearly this function is undefined at x equals 8. Okay, that's where it's undefined. You have a vertical asymptote here. So vertical asymptote at x equals 8. Okay, and again, you're not looking at this on a calculator, so if you're coming from the right of 8, you got to figure out if it's plus or minus. If you've got a vertical asymptote and you're interested in doing a limit around a vertical asymptote, your answer is either going to be plus or minus infinity. You just got to figure out which. So what I'm going to do is I'm going to let x be, something just a little bit to the right of it. It could even be 9. I'm just going to use like 8.1. And if you take your function 1 over 8.1 minus 8 squared, well, you're going to get you have a positive numerator. You already have a positive denominator because it's squared anyway. So that's going to give you a positive function value. So that means the answer to this problem is that's going to approach infinity. So what's really happening on this particular problem is you have a function that's really doing this. Okay, at 8, way over here at 8, you've got a vertical asymptote. Okay, you have a horizontal asymptote of y equals 0 because the degree of the top is less than the degree of the bottom. The degree of the top is 0, degree of the bottom is 2. So you also have this, and you would end up having a graph that does something kind of like this. Okay, both the left-hand limit and right-hand limit would approach the same value, and that's because you have a positive value. No matter what you plug in to the denominator other than 8, you're going to get a positive answer. You're undefined at 8, but every other thing you plug in for x guaranteed to give you a positive answer. So that's how you would reason out that the value of that limit goes to infinity. Okay, you want to study that. Okay, the next one, we're going to find all the vertical asymptotes. So one of the key things is, again, you have a rational function. So if you're going to find a vertical asymptote, you want to be sure that you simplify this first and see if anything cancels. So I'm going to go ahead and just factor this. The numerator does not factor, but I can take an x out of the bottom. So I'm focusing on factoring the denominator there. So if I do that, I take an x out, and I'm going to have x plus 64. There's no cancellation, so there's no hole in here. So all you should have to do is just set x equal to 0, set x plus 64 equals 0. So you're going to have two asymptotes. You're going to have x equals 0, and you're going to have x equals negative 64 as the two answers to that problem. Okay, so again, be sure that you factor and cancel, because if something canceled, then that wouldn't be an asymptote anymore. It would be a hole, like we've learned. Okay, so we have this. Okay, now the next one we're going to be looking at a couple of limits as x approaches infinity. And these kind of things here are totally dependent on knowledge of rational functions, basically. So what's going on this problem is, the numerator is going to go to infinity. You're going to get an infinitely large denominator here. Now what happens is the numerator, you really have a cosine, and that cosine, if you think about a cosine of 2x, really those function values are going to vary from -1 to 1. A cosine has a max of -1 and a minimum of 1, so really this numerator is going to be some constant that's going to vary. But the thing is that the denominator is going to 0, so anytime you have a constant over something infinitely large, that goes to 0. Okay, so the answer to that limit is going to be 0. Now you could use your limit laws if you wanted to. You could take that constant out, and you would have -100 limit x goes to infinity of cosine of 2x over x. It doesn't matter. It's still, this thing right here is just going to be a constant over infinity, so it's going to go to 0. So that's how you reason that out. You have to have knowledge of graphs and how functions behave. Okay, the next one, again, you're looking at a limit as x goes infinity of a rational function, so you kind of get interested in the horizontal asymptotes. So what we have on this is the degree of the numerator is going to be the highest power, that's going to be 3. The degree of the denominator is again the highest power, which is also 3. So we learned we had this rule basically that said if the degree of the numerator and denominator are the same, which they are, then y equals the ratio of the leading coefficients is going to be what that asymptote is. So the leading coefficients are 7 and -5, so the horizontal asymptote is going to be at -7/5. We just have a negative answer there. So that means the limit is going to approach the value of that horizontal asymptote, which is -7/5. Very easy problem if you know how the asymptotes behave. So that's what would happen in that particular problem. I'm testing you on the asymptotes, basically. Okay, the next one, you can use the limit laws on this. I think the limit laws come in very helpful on some of these problems. So this one, I have a limit of a quotient, so I can do the quotient of the limit. So I can do the limit as x goes to infinity of -1 plus 7 over x. Then I can do the limit as x approaches infinity of 6 minus 1 over x squared. Okay, now I'm going to go ahead and break it up. We can do a limit of a sum as the sum of the limits. So we would have the limit as x goes to infinity of -1 plus the limit as x goes to infinity of 7 over x, which is easy to reason out. Then we have a limit of a difference, so we can do the difference of the limit. So we have the limit x goes to infinity of 6 minus limit x goes to infinity of 1 over x squared. So now we can work this out. So basically you have these things. Okay, the limit of a constant is just that constant. So you're going to have -1 there and you're going to have 6 there. But this right here, we learned that basically what we learned is if you do the limit as x goes to infinity of a constant over some power of x, okay, that can be x to any power, then that thing is going to approach 0. Okay, because what you have is you have some constant over infinity, and that approaches 0. So that's going to go to 0. This one's also going to go to 0. It's the same structure. You got 1 over infinity squared. So it's 1 over infinity, it still goes to 0. Okay, like that. So that means when you do the arithmetic, that's -1/6. So then this would be the solution of that then, okay? All right, so that would be the answer and how you get that limit figured out. Okay, so moving to the next thing here, we got a couple of more limits to look at. Okay, this again is a rational function. Okay, so we're going to look at the degrees and we're going to look at the horizontal asymptote. So what we have is we have the degree of the numerator is equal to 2. Okay, that's the highest power. Okay, the degree of the denominator, the highest power, is 5. So by looking at this, okay, we had a set of rules that we learned. And what you notice on this, and this should be the degree of the denominator, okay, the degree of the denominator, so we have the degree of the numerator less than the degree of denominator. That means you can conclude that the horizontal asymptote is y equals 0. So that means the answer is that's going to go to 0. It's a rational function. Typically, you might look at the horizontal asymptote, so that's how I figure that out. Okay, and then the next problem on here is limit. Let's start by plugging 0 in. So you would have square root of 9 plus 0 minus 3 over 3 times 0. Okay, that's square root of 9 minus 3 over 0. That's 3 minus 3 over 0. So that is a 0 over 0 limit. So we need to do some sort of some algebra on this to make this work out. Okay, and we've talked about how to work with conjugates. So what we're going to do on this particular function is we're going to try to get rid of that radical in the numerator. So we're going to accomplish that by multiplying the numerator by the conjugate, 9x plus square root of 9 plus x plus 3 over square root of 9 plus x plus 3, like that. So we're going to multiply that out. Okay, so if we do this, and we got to do this carefully, we'll have the limit, x goes to 0. Okay, you can FOIL this out if you need to, or you can just square it, because what we have is a. If we have a minus b times a plus b, that's really just becomes a squared minus b squared. So you can just square both of these, and you can do this in your head. So if we square the first term, we're going to have square root of 9 plus x squared minus 3 squared. Then the denominator, we're going to leave that alone. Okay, so that's going to leave us with the limit as x approaches 0 of 9 plus x minus 9 all over 3x times the square root of 9 plus x plus 3, like that. Okay, you do have a cancellation. Okay, so that's going to leave us with the limit as x goes to 0 of x over 3x times the square root of 9 plus x plus 3. Okay, then we can cross out the x's, like that. Okay, so that's going to leave us with the limit as x approaches 0 of 1 over 3 times the square root of 9 plus x plus 3. So now we're ready to just try to reevaluate the limit and see what we get. Okay, so if I plug this in, I'm going to have 1 over 3 square root of 9 plus 0 plus 3. Then that's going to be 1 over 3. That will be square root of 9 plus 3 when we do that. Okay, so that's going to be 1 over 3 times 3 plus 3. So that will be 1 over 3 times 6. So the answer looks to be 1/18. Okay, so that's a lot of algebra going on that. I expect you to be able to handle conjugates. That will kind of help you prepare for some things you're going to do when we're learning about derivatives also, which should be beneficial. Okay, moving to the last page, you got the answer, so that should be the end of it. These would be the kinds of things I expect you to do on the first part of the exam.